Okay, let's get started. Today we're going to look at assignment 2. And this is preparation once again for the quiz on Monday. On this assignment you were supposed to write out your answers. You didn't need to necessarily compile and run your solution, just write out the solution and submit that directly in Blackboard, not through Subversion. But today I'm just going to work as we normally do, logged into a lab machine, and we'll work in that environment. But on the quiz you won't have access to that environment. All right, so let's take a look at this. This is it's one big chunk of source code. Yeah, you should do this on paper. I mean, you can do it. I think you should do it on paper to practice for the quiz and for the final. But you can also, in addition to doing it on paper, you could also, do it on one of the machines and just test your solutions to see that it works right. So that little bit of extra practice is good. Okay, so here is exercise 1. Draw the UML class diagram for the bean jar class. Let's take a look here. So, it's probably worth reading a description of the class here before we start the exercises. Instances of the bean jar class represent bean jars of varying capacity. The class provides functions to add beans, remove beans, and get the number of beans that are currently in the bean jar. The functions to add and remove beans return a Boolean value that indicates whether the operation succeeded or failed. When one of these functions fails, the number of beans in the jar will not have been changed. In other words, if a bean jar, or it should be, for example, if a bean jar has a capacity of 10 and there are 9 beans currently in the jar, then calling add beans 2 will return false, and the number of beans in the jar will remain at 9. Did we do the bean jar class some time ago already? We did, right? We didn't do it. We talked about it, but we didn't go through it. Okay. All right. So the first exercise is to draw the UML class diagram, which is straightforward if you look at this declaration section. So all the information that you need to do the UML class diagram is right inside here. So we declare the class. We have an open brace here. We have a closing brace followed by a semicolon down there. And then in between those two braces, we have all the information that we need to complete the UML class diagram. So let's go ahead and do that. Let's see, to make it easier, I'm going to copy an existing class diagram. So that would be, I think, is it lab 6? There we go. Just I'm going to copy that. So there's 3 regions in the UML class diagram. And the first region contains the class name, which in this case is bean jar. And the second region contains the member variables. And the third region contains the member functions. I think we'll need a few more there, so I'll just do that. So we have a public section and private section, and there could be member variables in either of those sections and member functions also in either of those sections. But generally the member variables will appear in the private section because that's a design pattern that programmers tend to use. They hide away the internal state of the class, which is recorded by these member variables. We hide those away as private data, and that we let the outside code outside of our class, modify our state, influence our state by calling functions, which are sometimes referred to as behaviors. Let's go ahead and put these, well, we'll do it one at a time here. There's one member variable, max number of beans, and that is that's private, so I'll use a minus sign to show that this member is private. And the UML class diagram syntax is different than C++. In the UML class diagram syntax, we list the data type after the function or the variable. So there we have max number of beans. That's the maximum number of beans that the jar can hold. That's the capacity of the jar. And here we have number of beans. That's how many beans are currently in the jar. So number of beans will have to be less than or equal to the max number of beans in all cases. That's a natural constraint. So those are the member variables right there. And now we can list the member functions. This is a special function here. This is called the constructor. And this function runs when instances of the class are created. So the purpose of this function is to initialize the state of the object that's created out of the class. It's good if you can keep the constructor very simple. So the constructor would simply be, we would pass this information in, the capacity of the jar, the number of beans that are currently in the jar. That information gets passed into the constructor. We set our two member variables to those values and then return, and that's it. So it's a very simple process. The constructor normally should be just a matter of setting up that initial state with the simple assignments, but it's not always that simple. So here is the constructor. This constructor is public. Some constructors are private. Looks like we're going to run out of space, so we'll have to modify our diagram. Maybe that's enough room. In VI, when I do an operation like that, just for those people who are using VI, then I can repeat my operation. I just press the period, just pressing dot here. So I just basically, when you perform an operation, it records it as a replayable macro. You just press dot. That's one of the. There's a lot of conveniences that you get with VI, but it is hard to learn. So, all right, there's the constructor. The constructor, it takes two arguments. both of type int. And now we have this, I think the book calls that a predicate function, or anything that returns a true-false value is a predicate. And this is add beans, remove beans. Let's go ahead and put these in there. Get number of beans. All right. Once again, add beans as a function returns a bool, so we list it after the function. Number of beans to add is a parameter in the function. So once again, that the parameter list has an item in it of type int, so that's listed after the parameter name. That gives us that function. I think they're all public. That's add beans. This is remove beans. Remove beans is bool. So the UML diagram, I mean, the purpose of it is to convey in, a simple view, a simple diagram, the behaviors, the nature of the class, and what are the behaviors and the state that it contains. All right, one more to go. Get number of beans. That's public. The function is get number of beans. It takes no arguments, and it returns, obviously, get number of beans is going to return an integer. And there it is. That's our UML class diagram. Yeah.
The parameters or the arguments inside of the function, why aren't those considered member variables?
The member variable, that's a good question. These variables that appear in the parameter list of a function, their scope is just inside the function itself. So this number of beans to add variable, which gets passed into add beans, is visible to the code that's in the add beans function, but is not visible to the code that's in the remove beans function. So it's the scope of visibility. They call that variable scope. So the parameters passed into a function, they exist just for the time that the function runs. So when you enter the function, the variable is created, it's used. When we return from the function, the variable is discarded, no longer exists. So in fact, another function, which you might call next, wouldn't have access to that variable. In fact, it was discarded already. But the member variables are not discarded. So once we call add beans, and we modify number of beans, and then we return from add beans, the member variable number of beans remains intact. So that when we call another function in the class, like remove beans, that function has access to that member variable number of beans. And once again, it utilizes the parameter number of beans to remove during its temporary existence. So number of beans to remove temporarily exists at the beginning of the function execution and is discarded when we return from the function. But the member variables, number of beans and max number of beans, those are not discarded. They continue to exist. Still hard to understand, right? But maybe a little bit more clear? Okay. All right, let's let's go forward. Here we have some implementation. This is in fact, you know, this a simple process that's normally carried out in a constructor. Max number of beans is passed into this constructor function, and we take that max number of beans and we copy its value. And remember, this max number of beans being passed in exists only for the execution of these two lines. And then after these two lines are executed, this max number of beans that's passed in, that variable, that memory slot, that 4 bytes in RAM, that's what it is discarded or is ignored or is allocated for another purpose. So we take that max number of beans that's passed in, the 4 bytes that are in memory, in RAM, and we copy those 4 bytes into the other 4 bytes that are allocated to store the member variable max number of beans. And notice they have the same name. So we want to be able to distinguish between the two of them. So we use this followed by a hyphen and a greater than symbol. Looks like an arrow. That's the symbol that we use to label the member variable and distinguish it from the parameter, the function parameter. Once again, the purpose of the constructor is to initialize the state of the object. And the state of the object is wholly represented by the value of those two integers. Functions have no state. They don't have any memory of anything. The only memory that's going on in this class is what these numbers are set to, what these variables are set to. That's why it comprises the state of objects that are created from this class. All right, we need to implement add beans. This is problem 2. So we pass in the number of beans to add. So it'll look something like this. We're going to take the current number of beans and add to it the number of beans to add. We could do this. Well, let me do this. So we'll do plus equals, so add into, so we have number of beans to add. Number of beans rather is a variable, and it has a number in it, and we want to add into that value the number of beans to add. Now we could use this like that. That's okay. We can do that. Actually, some people just do that automatically. They think it's easier to read the code because, oh, number of beans to add is a member variable of the class. But if we omit that, it works too. And the reason is that there's no parameter called number of beans here. So there's no ambiguity about what we're referring to. But in the constructor, the parameter name is identical to the member name, and so there is an ambiguity. When I use that name, which memory are we referring to? The locally scoped memory that's used to store the value of the parameter coming in, or the memory that's used to store the member variable? And the rule is that the variable, the parameter variable, has precedence. So if we don't say this, then when the compiler sees a name that exists in the parameter list, it's that piece of data. It's the parameter. But here there's no ambiguity, so we can just use number of beans. Now this would be the simple way to do it, right? We just say number of beans and we add the add into it the number of beans to add. But the problem there is we may be exceeding the capacity of the jar. So I have to check for that. In fact, we have a test. Here's a bean jar that has a capacity of 10 and 5 beans in it. That's the initial number of beans in the jar. It's half full. And then we call get number of beans just to make sure that our get number of beans function runs correctly. It should return 5. And then we add 3 beans, and then we call get number of beans. It should return 8. So now we have 8 beans in the jar. Now we call add beans with 4. I mean, 8 plus 4 is 12, but that exceeds the capacity of the jar. So add beans should return false. So we negate the false value so that we pass into assert a true, so that we don't terminate with a failure message. Because we want add beans to fail when we pass in 4 at this point. And then we test, we verify, yes, indeed, the number of beans in the jar remains the same because we can't add 4. Now, right now, we have stubs. Oh, here we have get number of beans. Look at this. This is a function that implements get number of beans. So look at get number of beans. It's a function. It takes no arguments. This is called an accessor function. It's just accessing one of the values inside the class. Get number of beans is a function inside the bean jar class. That's why we have this notation here. The function name is qualified with the class name. And then we have the return type here. It's an int. So get number of beans returns an int. So we have a single, simple statement. Return number of beans. So this is already implemented for us. That means this constructor we have implemented. Get number of beans is implemented. So this assertion should succeed. This assertion should succeed here. Well, both of these. But this one should fail. Oh, we didn't finish the implementation. We did add beans, see, but we need to return a bool. So we added the beans, but we didn't return anything. So let's return true and say, yeah, we succeeded. We added the beans. Of course, that won't be the case when we try to add 4. So we want to make sure that we get a failure here. So this line right there should fail because we're always returning true in our partial implementation. Let's see it fail. It should fail right there. And I want all of you to notice that all of the code is inside main.cpp. We haven't split it out into, beanjar.cpp and beanjar.h. We didn't do that. So this is a simplified format just for, doing the assignment and taking the quiz. But normally you would split out classes into those implementation files and header files. All right, let's see that. There it is, in fact. That's the assertion, not beanjar.addBeans4. That assertion failed because addBeans4 is returning true. So let's fix that. So we don't want to do this operation if it results in too many beans. So we could do it like this. If number of beans plus number of beans to add, if that is greater than max number of beans, well, that's a failure, right? Then we can return false. Else we'll do the operation and return true. You see how I'm indenting here to show how the logic, how these statements are conditioned on the result of the if condition. So the execution of these pieces of code are conditioned on the evaluation of this if condition right here. If this is true, we do this. If this is false, then we do this. And we show that logic with these indentations. It's not for the compiler, that's just for the human to read. And most of you know this already, but I'm repeating it because some of you are still not diligently indenting your code to show this this logical structure, and what you need to do in this course. So if the number of beans, see, we're not actually, look at this expression. It's different than this. See, this, here we're just adding the two things together. And then this gets evaluated as a sub-expression. This does not modify the state of number of beans. That's different than this operation. This operation modifies the state of number of beans. This expression here simply evaluates to a value, and then that value is then compared with this other value. And if the value on the left is greater than the value on the right, then it's true. That means we're trying to put too many beans in the jar. So we want to return false and do nothing. We don't want to put any beans at all in the jar. I think that should solve the problem. And it does. Any questions on this? Yeah.
What if you put the number of beans is greater than max number of beans, and you return false, but you put in number of beans is minus equals number of beans is that, so it subtracts back the amount, and then you return back the 8.
That's an alternative implementation you're suggesting? So add in the beans, and if it's bad, then subtract them out again? Yep, that's good. You can do it like that. You can do it like that. So there are different ways that you can implement the function. One way is to go ahead and add all the beans in there, modify the member variable, and then check the member variable to see that it's under the capacity. And if it's not, then let's take those beans out again. So you can do it like that. That's fine. So as usual, there are many different ways of implementing the functionality that we want. The question is, which way is easier to read, easier to maintain, easier to extend and modify later on? So your decision about how you're going to write the function doesn't have to do with whether it currently will run correctly or not. It has to do with whether in the future, when you or someone else looks at the code and needs to modify it or simply needs to understand it, that the function is implemented in as easy a manner, in a manner that's as easy to understand as possible, without sacrificing too much efficiency. Because sometimes it's easy to read something that's not done in an efficient way. In that case, the value of readability is trumped by the need to be more efficient. But that's a judgment call that you make. All right. Let's go on to remove beans is implemented, and here's problem 3. Add code to test the remove beans function. Make sure that the test code executes all lines of code in the remove beans function. So look at remove beans. So that means when our test code calls remove beans, we want to execute this return false. We'll always execute this if statement because it's the first line in the function. It always runs. But we want to enter into this block and return false, and then we want a separate test that enters into this block and returns true. All right, that's a requirement. That's a concept called test coverage. So good test coverage means the tests execute hopefully every line of code. And if your tests don't execute every line of code, then you have poor coverage. All right. Let's test this. Well, let's read it first. Actually, sometimes it's easier just to read the code than it is to go back and read the documentation about what the function does. And this is a case here. So we're passing, so the name of the function, remove beans. We want to take beans out of the jar. Okay, that's clear. And then the argument, number of beans to remove. What? The variable's long. I mean, it wouldn't be nice just to try to type in an X there and save a little time? Well, that'll save you time in that one moment, but later on you're going to waste a lot more time because you can't read the code. You've got an X here, a Y there, a J and an I here, and let's have a comment next to the X that says what it is, but let's say the comment is up in the beginning of the file. So let's just forget about adding a lot of unnecessary comments, choose longer variable names, identifier names, and let the code be self-documenting. So if the code can be self-documenting, that's what you want to try to achieve. So the number of beans to remove, that value that's getting passed in, that's how many beans to take out, right? If that's larger than the number of beans that are currently in the jar, we can't do it. Let's return false. On the other hand, if number of beans to remove is less than or equal to number of beans, then we can take those beans out, which we do here, and then we return true to indicate that the function succeeded. Let's create two test cases that test both of these execution paths. We can either reuse our existing bean jar, or we can create a new bean jar instance. And I'm going to show you how to do this by creating a new bean jar instance, but that's not necessary. But I want to show you that classes are intended to be used to create multiple instances. In fact, we'll just grab all of these. Here's the, well, I'll put it up here. Let's call this bean jar 2. And we have our tests in here. I just want to do this incrementally, make sure the test code gets done correctly. And let's suppose we pass in 100 this time. And the initial number of beans is 5, or is say 55. And we'll add beans 3, and then we should get 58. And here we'll add beans 54, and that should fail, right? So we give us 102. No, 112 rather, huh? Yeah, we should be removing. That's correct. But I'm going to build the code incrementally. So first, I made a copy. I want to make sure that what I copied runs, and then I'm going to go in there, and then I'm going to modify a little bit to remove beans instead of adding beans. All right, so, the copy is okay. I just want to make sure that we didn't mess up the copy. So we've got 55 beans in the jar. Let's try to remove beans. Let's remove 15 beans. So make it easier to do the mental arithmetic here. And that's going to be 40. Right? 55 minus 15 is 40. Now we have 40 beans in the jar. let's try to remove 41 beans. Oop, we don't want to add beans here. So when we try to remove 41 beans, that should fail. And the total number of beans should remain unchanged. Does that look good, the test? Well, now we had the benefit of having the compiler right here on the computer, but on the quiz you're going to have to mentally check this. So you're going to need to mentally execute the code and look for your own bugs. So after you come up with your answer, go back and do like you did in quiz 1, is you just mentally carry out the instructions in the program and see if there are any bugs in your solution. All right, exercise 4. Provide an alternative implementation of add beans. And this alternative implementation sets the number of beans in the jar to its maximum when the beans being added exceed the capacity of the jar, or the available capacity rather. It should continue to return false. So in other words, if we have a 10 bean jar, let's look at the source code here. If we have a 10 bean jar like this, and we have 8 beans in it, which is the case here, and we try to add 4 beans, that's still going to return false to tell us there's a problem. But it's going to max out the number of beans in the jar. It'll set it to its maximum, which is 10. Does that make sense? So let's test it. This is going to succeed. This will succeed. This is good. But this is the function that's being modified. Well, that's the function that's being modified too. And this should continue to return false. But this statement should fail because we didn't change the implementation. So let's see that line fails. And look, it's line 101. There it is, line 101. Bean jar, get number of beans equals 10, failed. So we don't have 10 beans in the jar, which is what we want with our alternative implementation. So let's go up here and do that. So we want to continue. We're detecting the bad case right here. This is where that's being triggered and we're returning false. But we want to set the number of beans in the jar to its capacity to show that it's full. But we'll return false to show that we return false to show that there was a problem. We discarded beans. So this should hopefully pass. There it is. Okay. Exercise 5 is similar. Provide an alternative implementation of remove beans that works in a similar manner. So let's go ahead and do that. Well, let's do the test first. We're going to do test first development. The bean jar has a capacity of 100. It's initially set to 55 beans. Get number of beans should return 55. Remove 15 beans, we're going to get 40 beans. Try to remove 41 beans. This should fail because trying to remove more than we have. But when we call get number of beans, we're going to have 0 beans now because we did as much as we could. So this spot is going to fail right there. This is line 115. And there it is, line 115, number of being 0. All right, now that we have our test code constructed, let's go ahead and implement the function to pass the test. So here is remove beans, and here's the problem here. We're correctly returning false, that's all right. But we want to modify the number of beans in the jar. Set it to 0. We're going to take every last bean out of the jar because we want to remove even more beans if we could. All test passed. There we go. So that's it. That's not too bad, right? But now the quiz, I'm not going to give this question on the quiz. I'm going to give a different question. I'm not just going to give you this question. I'll just give you an A right now. How about that? How does that work? So you have to understand what we did. Just can't memorize the bean jar class. That doesn't work, right? You have to understand how the whole process and the concepts behind what we're doing. You know, we had some other classes, other exercises that you should probably look at. Was it Lab 6? You know, this number class. I like the number class. Maybe we put something in there that has to do with the number class. Oh, I got an idea right now. I think I have the quiz in my head. I think I might have you implement the number class, but I'm not going to say what I'm going to ask. Maybe. It's just an idea. Okay. Any questions? Do you want to look at the number class again, or? Yeah?
Can you go over the? I'm still having trouble with the asserts with the exclamation point with the negation in front.
Yeah. See, the thing about assert is, and we have it right here, right? We create an instant. We have a number. The instance of the class is 27. We call it 27 in words. All right. To distinguish it from 73 here. Okay. So we have a class. We make multiple instances of the class. We got to give them different names. So this one is called appropriately 27 because that's what we passed into the constructor. And then we call is prime. Then, well, 27 is not prime. So it's divisible by 9 and 3. This function should return false. So this expression here, that expression exactly that I have highlighted, should evaluate to false. So the assert, that's all we passed into assert. Assert is going to say, oh, false, false. I'm going to terminate right here and present an error message to say that you passed in false to me. I'm going to terminate.
So assert should always come back true unless you put the negation.
Your goal is to only pass in true to assert. If you pass in false to assert, you're going to terminate with an error message. Like, I assert it is not raining today. An assertion is a statement of fact, and it may be false. And you want to know when your program is lying to you. So, and their purpose of that is to catch bugs, to verify our reasoning about the code. So we use asserts to verify our reasoning about the code. And I want to tell you, you will be surprised at how often your assertions will fail if you use them regularly. And it will save you a lot of time in the long run. because you'll catch failures in your reasoning at an earlier point in time rather than at a later point in time when you're doing some debugging. So that's anything else you want to look at this, or let's take a look. Let's go into lab 6. Is it 6.2 or 1? I can't remember. That's that web page. So here it is. We're on the quiz. I'm not going to have a .h .cpp. I mean, it doesn't really make sense. Just the whole thing will be there, and but you'll see there will be this element of testing with assertions. So you need to know that, and you'll need to understand how to create instances of your class using this syntax here. The constructor, the class name. It comes first. That's the data type. Just as if you were to declare an int, int argc up here. You have number 9. So the variable name is 9 with a lowercase n. Class name is uppercase n here. That's a convention, not a requirement. And the constructor will take 0 or more arguments. And then we have assertions to test our code. And one of the things we want to accomplish with the assertions is we want to call functions or do operations that end up executing all possible execution paths in the code. So inside a function, if you have a branch, which is an if statement, if x is greater than 0, then do this, else do that. You want to have at least 2 tests there to execute both of those paths through the logic. And there's the UML class diagram. On the quiz, I will have a class that requires 1 or more member variables. So that web page problem is unlikely because it didn't include, a member variable. So this is a better illustration of what a class would look like. It has at least 1 member variable. Typically, in this class, all our member variables will always be private, which many people consider good practice. And some of the functions may be private, but in this case, they're all public. Remember about the syntax. The data type follows the identifier, whether the identifier is a variable or a function. So I use the word identifier. That's a more general term than the term function name or variable name. Function name and variable name are 2 types of identifiers. And this int here, this is an identifier, but it's not a function name. It's not a variable name. It's a built-in data type. And here's the class. We don't provide any implementations in the declaration, although we could. The constructor has no return value, because actually what you get is an instance of the class. So, maybe they could have declared it like that. A calling number gives us a number. But that's not how they do it. So when we use special syntax to create instances of classes that look slightly different from the syntax used to call functions, just a little bit different. See, here's the function. We're not saying 77 equals, number parentheses 77. We didn't do it like that. So we use this special syntax here. And so the syntax for invoking a constructor, you have to memorize that. Yeah, question? Why do we put the semicolon at the end? These are called declarations. This is a statement that is prime, is a function, it exists. I'm not going to tell you what it does. I'm not going to give you the implementation. I'm not going to give you the details. I'm just telling you that there is a function called isPrime and it returns a bool. And the semicolon tells the compiler that, oh, that's the end of the declaration. Because in fact, you can add different things following the function name. I think, did the book talk about const? Oh, I should have talked about const. I didn't get to that. So you're not required to know about that. And that when we call the function, is the const appear? I don't work in C++ regularly. Do we put const after the function name or before it? It's after. And this is in fact how we should declare these functions. This is in fact this is how a good programmer would declare those functions. And that const, it's a message to the compiler. It tells the compiler, hey, when code calls isPrime, it'll do something and return a value, but it will not modify the state of the object. So that means there's only one member variable, n. That means n will not change. So the compiler will look to see that isPrime, that when the code, it has no statements in there that will modify the value of n. And this is like basically this is an assertion. In your reasoning, isPrime shouldn't modify n. So we put it in there as an assertion because what if, someone else implemented isPrime, and I'm the project manager, someone else's job was to implement isPrime, and I put const there because I know, and everybody on the project knows, that isPrime shouldn't modify the state of the object, represented by n. But I put it in there just to be safe, because what happens if that programmer actually did modify n? Then it wouldn't compile, and then we would catch the bug. Let's take a look at that. This should fail to compile. Well, not because we're modifying n, but for a different reason. We need to put this in there as well. It works. Whoops, that's CI. This is this should be, this compiler, there's something, the default settings are too generous. There must be a setting that that catches this mistake. The compiler normally would complain that there is no function isPrime that is declared as const. So that's a problem, actually. Oh, What's going on there? So this is prime is declared as const, is divisible by is const. I don't, so anyway, this is how to do it. This has to be const as well. Maybe that's the problem. And we're running out of time, so I don't have time to investigate, but what is going on here? Alright, anyway, it's not going to be on the quiz. I have to spend time thinking about that. Yeah. Okay, I think that's it. Okay, we'll see you on Monday.